Hi, Algebra 2. Here is our videos for section 5.2. Here we're going to be covering, we're going to go ahead and evaluate and graph polynomial functions. Okay, so our objectives for that are to identify and categorize examples of polynomial functions. All right, so just taking a look at what a polynomial function is, that should kind of be review. But then we'll look into some new types of polynomials. We're already familiar with a few of them. And then we're going to evaluate those polynomial functions. You should be familiar with that as well, at least with the ones you're familiar with. And then we're going to determine something new called end behavior of the graph of a polynomial function. And we're going to do this from both the equation and the graph, like I said. Okay, so let's start off with just what a polynomial function is. What are some characteristics of it? All right, so let's start off with just looking at what it looks like. Okay, so a polynomial function looks like this. So it's a function, we got f of x, and it looks something like we have a sub n times x to the nth power plus a sub n minus 1, so n minus 1 in the subscript, x to the n minus 1, n minus 1 in the exponent. And then that kind of descends, that keeps going until we end up with a sub 1 x plus a sub 0. All right, so it's kind of a string of all these terms. Remember these terms, they're called monomials, right? Because monomials are kind of single term things that go into a mathematical expression, right? So then a few characteristics that we want to keep track of, right? So the first one is that all coefficients, and by coefficients, I'm talking about these a's, the a sub n minus 1, a sub 1, a sub 0, right? So just to kind of make sure it's hammered in, that is a sub n minus 1 in the subscript. It's not a sub n minus 1. Okay, that's not it. It's a sub n minus 1. This just means that we're going down. It's 1 less than a sub n minus 2. It's 1 less than 2 less than a sub n, etc. Okay, just to kind of clarify that. So all coefficients are real numbers. So all the coefficients in our polynomial are real numbers. 2, all exponents are whole numbers. Okay. So our exponents have to be whole numbers. So like 1, 2, 7, 11, 10, right? No negatives. All right. So, and then no fractions, no negatives, no fractions, no radicals, no pi, etc. Okay. All whole numbers. All right. Our third is that always want in a standard form. Okay. So that means organize by exponents from least to greatest. Okay, and we'll see what that means. Don't worry. To greatest. All right, and then another property that will kind of be useful here is, we have a few more. The a sub n is not 0. We don't want a sub n to be 0 because then there's no point in putting it there. The other ones are okay. It's okay if the other ones are 0. But a sub n particularly should not be 0 because otherwise we don't have that specific polynomial. Okay, a sub n is 0, and a sub n is called the leading coefficient. Okay, and I'm going to highlight that. And you're going to want to remember what leading coefficient is because we're going to need it for the rest of this section. Sorry, I can't draw straight lines apparently. Okay, we're gonna need it for the rest of this section, really for the rest of this chapter. All right, a spin is called the leading coefficient. Okay, so number 5 in our list of properties, the highest power. So the highest power, this is all, that's another word for exponent. The highest exponent is the degree. Okay, that's another term, the degree. Okay, so the degree of a polynomial is the highest exponent, the highest power, the biggest one. All right, and then one more. A sub 0 is the constant coefficient. And it also happens to be the y-intercept, always, right? So a sub 0 is our constant coefficient, and it's also always our y-intercept. And that might be familiar from when we did quadratics. The c in standard form was always our y-intercept. Okay, so go ahead and pause this video to copy this down because I'll actually be erasing it. I didn't account for all the space that I needed for this part, so I apologize. But go ahead and pause this video now if you're not done copying this down, or rewind it if you need me to read some of this out, because I know my handwriting isn't the best. But go ahead and rewind if you haven't finished copying down. I'm gonna go ahead and erase, that way I have more space to write a few more things down. All right. So the next thing we want to look at is just a few examples of some typical polynomial functions. So typical polynomial functions. All right, we're going to be organizing these by degree, not pedigree, degree. And actually, I want to use a different color here. We're going to use green. Feeling a little green right now. So degree. Still kind of looks like a P, but you get the idea. And then the name of the type. So name or type. And then some examples. All right, so have a table that looks like this in your notes. We're gonna go degree 0, 1, 2, 3, 4. We can keep going. We're allowed to keep going, but we really only care about 0 through 4 right now. Okay, so when a polynomial function has degree 0, so that means the highest exponent is 0, that's a constant function. Okay, so constant function. And that's because our constant functions, if the highest exponent is 0, that means we just have numbers. So f of x is equal to 2. F of x is equal to -7, right? These all look like horizontal lines when you graph them. All right, degree 1, you're familiar with that. That's a linear function, right? Degree 1 means that the highest power is 1, which means that we usually just have a power, just regular x. Okay, so example for that one, f of x is equal to, let's say, 7x. F of x is equal to -1/2 x plus 1, right? These are examples of linear functions. We've seen these before. These are the ones we looked at in chapter 2. Okay, degree 2, you're also familiar with those. Quadratic. Okay, quadratic. Those are the ones we studied in chapter 4. So we have ones that look like -x² minus 7. I'm using 7s a lot for some reason. F of x is equal to 2x² minus 10x, right? So notice that even though the polynomial is defined to be all these terms, the only term that's required is the first one, right? Because I can just have 7x. I don't have to have the remaining, like I can just have this term. I don't have to have every single thing behind it as long as I have that one. Same thing with the quadratic. I'm allowed to have the x², like I need to have that. And then I can have the x if I want, and I can have the constant if I want. I don't have to have both, as long as I have the x². it'll be the same for all the higher powers. So for degree 3, those are called cubic functions. F of x is equal to, an example could be x cubed minus 10, right? I don't have the x squared or the x term, but then I definitely could have all of them if I wanted to, right? So that's an example of a cubic function that has all the terms. And then the last one we really are going to focus on is called the quartic function. So f of x is equal to x to the 4th minus 7. I came with the 7s. I don't know why the 7 is the first number that pops up. 10x squared minus 11x plus 50. I did not almost just write 7, I promise. And then maybe one more example. I could just have 10x cubed minus 15x plus 2. I don't know why I said cubed when this is a 4th degree. That should be 4. Okay. So these are the types that we'll be kind of focusing on in this section, all right? So let's do a quick, actually, I think this video might be long already, so let's do identification in the next one, along with evaluation. So I'll see you in the next part.